Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. Now, I'd like to start off our event today by thanking Databricks for sponsoring today's event. Databricks is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Now, today's webinar is entitled State-of-the-Art Deep Learning on Apache Spark, and that'll be presented by Databricks. But before we begin, I'd like to briefly review the format for today's webinar. Today's event will be an hour long. We have one presenter who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation, and this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation, as we'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Xiangri Meng with Databricks. Xiangri's an Apache Spark PMC member and a software engineer at Databricks. His main interests center around developing and implementing scalable algorithms for scientific applications. He's been actively involved in the development and maintenance of Spark ML Live since he joined Databricks. Now, before Databricks, he worked as an applied research engineer at LinkedIn, where he was the main developer for an offline machine learning framework in Hadoop MapReduce. His PhD work at Stanford is on randomized algorithms for large-scale linear regression problems. So Xiangri, thanks for being with us today. We're looking forward to your presentation. Now, big data and AI are joined at the hip. The best AI applications require massive amounts of constantly updated training data to build state-of-the-art models. So increasingly, more Spark users want to integrate Spark with distributed machine learning frameworks built for state-of-the-art training. Well, here's the problem. Big data frameworks like Spark and distributed deep learning frameworks don't play well together due to the disparity between how big data jobs are executed and how deep learning jobs are executed. So in today's Data Science Central webinar, we'll share how Project Hydrogen, a Spark project improvement proposal led by Databricks, is positioned as a potential solution to this problem. So we'll cover barrier execution mode for distributed DL training, fast data exchange between Spark and DL frameworks, and Accelerator awareness scheduling. So Xiangri, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Thanks, Bill, for the intro and Data Science Central for hosting this webinar. Hi, everyone, and this is Xiangri from Databricks. Today, I'm going to talk about this ongoing initiative from Apache Spark called Project Hydrogen, and the goal is to bring the state-of-the-art big data and AI solutions together. A quick introduction about Databricks. So the company was founded by the original creators of Apache Spark, and we built a unified analytics platform on top of Spark and the cloud providers. So basically, if you want to get a quick way to learn Spark and machine learning or just a big data processing, and we provide the best platform for you to do that. And there's also a free version called Databricks Community Edition, which you can search online and try it out. So today I'm going to talk about two communities. And the first community is the big data community, and where Apache Spark is kind of the de facto standard engine for big data right now. And if you are a data scientist in a company that need to handle large or medium data sets or complex data scenarios, for example, like reading data from a stream or reading data from an encrypted data source, you're perhaps already a Spark user. And the Spark community is very large, and we also have meetups and conferences every year to talk about the recent features from Apache Spark. So the second community I want to talk about today is the machine learning and AI community. So everyone knows that AI is basically reshaping our lives. So when you take a photo and AI helps you to recognize the thing and make the photo better for you. And we all know about self-driving cars, smart home devices, right? So basically, we are living in an AI world already. And I think both community in the past few years came along with many feature developments. For example, Apache Spark in the past 5 years, starting from very primitive RDD API, and that can do just big data processing, and then the community added different language APIs like Python and R, and then just build up standard components like MLlib for machine learning, GraphX for graph processing, and then we released this data frame API to make it super easy for data scientists to use. And then we kind of introduced the project constant to bring the bare metal performance to big data processing and machine learning in Spark. So on the other side, when you look at the machine learning and AI community, they started with dedicated tools for training just a single family of machine learning models, like liblinear for linear models and GRMNet also for linear models and for R. And then they start building this general purpose machine learning package like the popular scikit-learn, right? So for the Python community. And then this many deep learning frameworks show up, like a TensorFlow, MXNet, and PyTorch. And then, so what we see the crossover is, we saw that AI actually needs big data. So in the lower end of the slides, we show this very popular chart. And with traditional machine learning algorithms, usually you see the performance do not just increase when you just adding new data to the training process. And because usually those algorithms can only represent a very limited feature space, right, function space. But with deep learning and the models can scale very well with the amount of data you have. So everyone wants a better prediction accuracy, more powerful predictive models, right? So, and that's why people want AI needs big data. People want more training data to get better models. And that comes the requirements to handle those big amount of data. We have seen some efforts from the AI community to handle different kind of data scenarios and a large amount of data. For example, the TensorFlow community, they build this tf.data package and tf.transform package, and that provides some basic data transformation to our data set. And then they release this Spark TensorFlow connector, right? So that can convert a Spark data frame into TF records. So basically, we see those efforts from the AI community and for handling big data. And on the other side, so, big data, we see the need for AI from the big data community. So Databricks has many customers and they collect tons of data, right? So we interviewed several of the customers and asked them why. So why they need big data. I think 7 out of 10 or 7 or 8 out of 10, you hear the answer is, I need to do machine learning, I need to do AI. I want to just use AI to power my business, right? So, and for that particular reason, we also saw many efforts from the Spark community to try to integrate Spark with AI and the machine learning frameworks. For example, the Cafe on Spark, TensorFlow on Spark from Yahoo, and the BigDL from Intel, and many other packages. And those packages are built on top of Spark, but built for machine learning and AI purposes. So, yeah, basically this is where we see the cross. Right, so we saw this overlapping efforts, and we saw more distributed deep learning training frameworks showing up, like a distributed TensorFlow and hardware developed from Uber and distributed MXNet. So basically, we want to think about what's the best feature or offering we can make for the data scientists so they can deal with this more complex scenarios easily. I want to talk about two stories. And if you're a data scientist, you're working with really large data sets, you are perhaps pretty familiar with those two stories. The first story is distributed deep learning training. So you want to build a pipeline that can fetch training events from a production data warehouse, right? So, and then you want to train a deep learning model in parallel. You want to do it in parallel because there's a tons of training data and it's too slow on a single machine, or you want to do hyperparameter tuning to get a better model. And after you have a trained model, you want to make a model inference, right? So the second story here is you want to apply a trained deep learning model to a distributed stream of events. And then you want to enrich it with predicted labels. For example, you receive a stream of new images uploaded by users, and you want to make predictions or recognize the objects in those images, and then send the prediction results as a stream to downstream applications, right? So those two are two simple stories if we talk about distributed AI and big data. And the problem comes when we think about what would be the underlying architecture, right? So the infrastructure we can use to support those two stories. Let's take a look at the distributed training story. First, you need to load data from a production data warehouse, right? So usually this is then maintained by a data engineering team. And you may need to read data from different data sources, for example, like a Databricks data and AWS S3, Kafka, or Azure Blob Storage, or even just a simple MySQL database or a CSV file, right? So, and you need an engine that can read data from different data sources. And Spark is the definitive answer here because Spark has many built-in data sources. And in the community, we also have 50 plus data sources. Literally, Spark can read data in from everywhere. And then after you load the training events and you want to fit a model. To fit a model, especially to fit a deep learning model, you need a GPU machines, right? So GPU can give you faster training. And if you want to do that in parallel, you need a distributed GPU cluster to get certain acceleration. But if you look at the answers here, so you need a Spark cluster for data loading, and then you need a distributed GPU cluster for fast training. So then, well, how to handle this infrastructure, right? So one simple answer is you just have two different clusters, right? You have a Spark cluster, you have a GPU cluster, and you use Spark to load the data and save the data in a format that can be loaded by the distributed deep learning framework. And then you fit a model on a GPU cluster, and then you output the model. But as a data scientist, you need to maintain the glue code between the two jobs, one on the Spark cluster and one on the GPU cluster. And usually they're not, they don't have just the same kind of job scheduler. You need to learn how to submit a Spark job. You need to learn how to submit a distributed deep learning job, how to group them together, and how to handle failures. And then you have a different kind of workflow for debugging. And basically, this just makes your life harder, right? So, and then let's talk about the model inference story. For model inference, you read the data from streaming data sets like a Kafka. And then you load those events in, let's say, images. You want to apply this model to the stream, and you also want fast inference to reduce the latency, right? So in this case, maybe you still want to use GPU for faster inference, but however, most of the deep learning frameworks like TensorFlow and MXNet, they do not support reading data directly from Kafka. So you need to kind of implement this connector and that's not a job for a data scientist, usually. So Spark can easily read data from Kafka, and if you can just say embed the model inference as part of the Spark job, and you can also use Spark to save the predictions back into this Kafka data, just a streaming data sync, right? So that would be an easy setup. But think about this. If you do this on 2 clusters, and then you need to pass the data over from Spark to this GPU cluster, that just makes this pipeline really awkward to set up. And you need to handle how you can pass the data over in real time by yourself. And there's no good engine to use, right? So for streaming model inference, apparently, well, we kind of need a single cluster to do the data loading, model prediction, and the data saving. So that's the status quo. And then let's think about this. How about let's just use one single cluster to handle both the Spark data processing and deep learning model training and model inference. And yeah, that seems the next setup, right? So if you can just use one cluster, you only need to learn one kind of, get familiar with one workflow. But unfortunately, I'm here to tell you, just it doesn't work out of the box. And I'm going to show you a demo and using Databricks. Let me see, go to share my screen. Okay, so I want to use a very simple example, and this is just recognizing the digits. I think many of you are familiar with this application. And this is a Databricks notebook, and behind it is a Spark cluster and configured in the cloud. So I just want to run those commands. So what those commands does is just load some utility, so we don't need to show you tons of code. And then we read the digits from a production table called mnist. So here we use Databricks data as the production data warehouse, but it could be just a different data source. And then I write those digits out as a Parquet format. And the next one I'm going to do is I'm going to use Harvard to start a training job. So Harvard is based on the MPI framework, and it supports TensorFlow, MXNet, TensorFlow, Keras, and PyTorch. And what we need to do is to run an MPI command, giving the worker IP addresses and your training script. And then the Harvard can launch an MPI job to do the training. And as you can see here, the training started, and I'm using 2 nodes here. And while the training is running, this is actually a 4-node GPU cluster, but we only use 2 workers. Well, can I just use the rest of the resources and do some other workloads? So let's switch to a new notebook here. And here I'm going to use the same cluster, but I'm going to run a streaming model inference job. So basically, I'm wrapping those the workload into some utility functions. I'm reading a digital stream, just a stream of the digits, and then I want to apply the predictions using GPU. You don't need to know the details and how I implement it. And you see, but basically, while this streaming job started, and then you see for the first batch, and you got 4 jobs running, and you try to make predictions. And now what you see here is it hit an exception, and the stream stopped. And what happens here is, hope you can read this clearly. So the error is GPU is occupied by another process. So this is the problem everyone may hit if they try to hybrid the distributed deep learning workloads and the Spark workloads together on a single cluster. And let me explain why. While we hit this issue is, let's go back to the slides. Yep. So what happens is Spark doesn't really know there is an MPI job running and doing distributed deep learning training, right? So it's a 4-node cluster. We use 2 nodes to run distributed deep learning training job. But however, because Spark doesn't know it. When Spark do this streaming model inference, Spark tries to use all the available nodes to Spark itself and to schedule those model inference jobs. Spark actually use 4 nodes instead of just 2 nodes. And so those 2 workloads just cross into each other. And then you see the error because the GPU is already occupied by the training process. So this is a fundamental kind of scheduling problem. And in order to make it work, we need to run the distributed deep learning job as a Spark job, such that Spark scheduler can recognize this workload and try to schedule resources on other worker nodes, so to avoid this collision. And however, this is not an easy task. That's why we need this Project Hydrogen initiative, and I will briefly explain why. Spark is a big data engine built on top of the MapReduce framework, and all the tasks scheduled by Spark, they are independent of each other. So each task can run, can fail, can be rescheduled independently. So that's why we can receive just say embarrassingly parallelism and massive scalability. But for distributed deep learning jobs, you need a kind of fast and frequent and coordination among the tasks. They pass over the messages frequently to update the model, update the gradient. And so they need to talk to each other. They depend on each other. So in case of failures, and Spark can just say simply recover the failed task. But for distributed deep learning training, and usually if one failed, and you may need to rerun all the tasks. Depends on the implementation, but this is just a general case. So in order to resolve those fundamental difference, and we propose this Project Hydrogen, and it contains 3 sub-projects. We call it Barrier Execution Mode, Optimized Data Exchange, and Accelerator Aware Job Scheduling. So let's first look at the Barrier Execution Mode. What it does is basically allow Spark to schedule jobs and that can fit for the distributed deep learning training communication pattern. So basically, with this barrier execution mode, we can tell Spark, for this particular job, please start all the tasks together and provide the user sufficient info and tooling to set up this hybrid distributed deep learning job. And in case of failures, if you see a failure on one node, and you can cancel and restart all the tasks in case of failures. So basically, this allows, on the scheduler side, allows to schedule distributed deep learning Spark jobs. And let's briefly look at the API. I'm using Scala here to demonstrate API, but we also have Python API, which is very similar. So first one, we introduce a barrier function to the RDD class. And basically, if you have RDD representing a distributed data set, and you can call RDD.barrier to tell Spark, for this stage, I want the tasks to be just scheduled together. And then you can say, just map partitions and to describe what you want to compute, right? So, and the next API and is within this task closure, and we provide a context of barrier function. And essentially, it tells the workers to wait until all the tasks in this stage hit this barrier. If you're familiar with the MPI interface, this is very similar to the MPI barrier. It's basically just say everyone waits, and the example here is every task can first write the partition data out, right? So and then set a barrier, and after this barrier, so all the data are ready, and please start the training job. So, yep, the next one will be the context get task info. So it's basically, it tells user where are the workers for this stage, right? So you can get IP addresses from this API, and then, well, you can use that to start a hybridized MPI job or start a hybridized distributed TensorFlow job. Those are the basic APIs we implemented in Spark 2.4. So with this API, we can actually have a more proper integration of distributed deep learning training job on Spark. So I'm going to show you another demo. So let me share my screen. Okay. Yep. So I'm going to run this demo on a different cluster and also a 4-node GPU cluster. For the training part, and essentially it's doing the same training job, but the difference here, instead of running training as a just simple MPI command, we embed the training as a Spark job here. As you can see, well, it actually starts a Spark job to run the Harvard training job, training workload, and then everything is integrated with Spark. As you can see in the Spark log, the training started, right? So, and now, while Spark understands that there is a distributed training job running on those 2 nodes, and then let's see what happens if we run the model inference job on the same cluster. And for this notebook, it's exactly the same notebook that hit an error before. And as you can see, when we start the streaming model inference, and the Spark only schedule 2 workers for each batch instead of 4, because now Spark Job Scheduler knows those 2 are available, but the other 2 are running some other workloads. So in this way, well, we don't have this workloads crossing into each other, and then you can use a shared Spark cluster to do both training and distributed model inference, and to use all the resources properly. So, and as you can see, well, let's wait for maybe 1 or 2 seconds. As you can see, you see the label and predictions, and you can monitor the streaming model inference job just at real time. So basically, this parallel execution mode allow we run distributed deep learning training workloads as an embedded Spark job. So you can use the same cluster to do both data processing and distributed deep learning training. And the next sub-project in this project Hydrogen is called Optimized Data Exchange. So basically, well, when we talk about big data and AI integration, well, none of the integration is possible without exchanging data between the 2 frameworks, right? So Spark and AI. And definitely performance matters here because we are talking about big data. And let me stop the screen sharing. So hopefully you can see my slides now. So basically there are 2 problems here. The first problem is we need to deal with many data formats. And we need to read data in one format, and before training, we need to convert it to a different format. For example, we have Parquet, Avro, sequence file, and then for distributed deep learning training, we have TF records, DSC, libsvm, right? So, and you can always implement an optimized conversion from one format to another format. But you end up with this n times n complexity, right? So you need to, once you handle RC to TF records, you may need to implement your own kind of converter, and that's not efficient. So one thing we can do is if we can put a standard interface in between, let's say Apache Spark for reading data in, and we propose just Apache Arrow is another Apache Software Foundation project as the standard interface for data exchange. And with this standard format, you only need to implement n+n+2 converters, right? You only care about how to get Parquet in and how to convert Arrow to a format you care for deep learning, let's say TF records. So Spark can already read many data sources, and then just we only need to say how to convert Spark internal data format to Apache Arrow, and then from there how to convert to this some deep learning compatible record format. So in this way, while you have a less complexity to handle, but because performance matters, we do care about how we can optimize the data conversion so it doesn't introduce just a big overhead. If there is a big overhead and people will try to avoid this data conversion path and do this optimized conversion directly, but then just increase the complexity. So this is one of the data exchange work, and we are going to use. And then the next feature we want to implement is vectorized computation, and this is for the model inference case. So you want to apply the model and to the input records and make some predictions. And one way to do it is you do this a row at a time prediction. Basically, you take one record and get into Spark, and then you apply the model, and it could be just expressed by a Python UDF, and then you make the predictions out and as part of the Spark output, and then you move to the next record one by one. So this is not efficient, and because especially for deep learning model inference, and you need special accelerators like a GPU for the model inference. And if you send records one at a time, and you cannot really utilize the computation acceleration. Even for CPU, it's not the best setup. So we want to vectorize the prediction. Instead of sending the records one by one, we send a row batch at one time. And then, inside this row batch, we store the data in columnar format. So actually, when we do the prediction, it got applied to the entire row batch and to a certain column, and then get the result out. So this is what we call vectorized prediction. And in Spark 2.3, we already introduced this Pandas UDF, and so it uses Apache Arrow for the data exchange, and it just uses Pandas data frames for vectorized computation. And you see there is almost 100x performance speed up. And to learn more about this Pandas UDF, you can just check there is a blog post on Databricks website to show its usage. And for this particular project, we also need to do this vectorized computation for GPUs, where we're going to do some data pipelining to avoid GPU waiting for CPU to load the data and send the data over. So that's also part of this optimized data exchange project. So the last one, the project under Project Hydrogen, we call it Accelerator Aware Scheduling. And essentially, we need to deal with just a heterogeneous cluster, and some of the nodes may have accelerators installed, like a GPU, FPGAs. And Spark needs to understand what resources are available on which nodes, and in order to schedule jobs properly, right? So, and for example, this is API in the current proposal is not finalized yet. So what you can do is you say this is not, tell Spark, this is not a normal data processing job, and I need some accelerators. And you can call RDD accelerated by a name. Say you can say GPU, or you can say with GPU with specific GPU models, right? So, and then you tell Spark, I need a 1 or 2 accelerators per task, and this is absolutely required for my workload. So basically it means do not schedule workload if you cannot find an available accelerator. So, or you can say this is optional. If you can find one, please use it. If you cannot, let's use CPU to do the work. So that basically help you to tell Spark how you want to accelerate your workload. So then with this, you can actually handle multiple accelerators on the same node. So each task knows about, from maybe there are 4 GPUs on a single node. This task knows which GPU it got assigned to, right? So the task only use those 2 GPUs, and then the task on the same node won't got across into each other. So that's the purpose for this accelerator-aware job scheduling. And the timeline about this Project Hydrogen features, in Spark 2.4, I think it will soon to be released. And we implement the better execution mode that can handle this basic scenarios and like the one I demoed here. And the Databricks, this is a Databricks feature. We're going to integrate better execution mode and with Harvard and to provide a smooth integration and for customers and users to run distributed deep learning jobs on Databricks. So, and then for the next version, maybe it's called Spark 3.0, and it's not confirmed yet. And we're going to just say make better execution mode into a production-ready state. It will involve supporting different cluster managers like Yarn, Kubernetes, and Mesos. And then the optimized data exchange, and we're going to just start doing the development and make the optimized data exchange into the next major release as well. And same for Accelerator aware job scheduling. And because this is an open source project, we need your help. And if you are a developer, you can just say, look at the JIRAs I listed in the slides, and you can just contribute your ideas and start coding and to help us. And if you're a user, you can tell us about the use case, and you can see if the implemented features or the planned features fit your scenario as well. If you see gaps, let us know. You can just send an email to users at Apache. I think spark.apache.org, that's the user mailing list. And yeah, just let us hear your voice and to help this project. So I want to thank the community. There's many community members, and this project is not really just made by myself. And I talked to many Spark committers and the developers, and which designed the project proposal and the engineering design and also the implementation. And the ideas are not new. It's also based on the previous community work, like TensorFrames from Databricks and BigDL from Intel and the Apache Arrow project. So I want to thank people who helped in this project. And lastly, because I mentioned that, well, we're going to provide integration with this better execution mode and Harvard on Databricks. I want to spend a couple of minutes to demo this upcoming feature. Let me share my screen again. Okay. So the integration we call Harvard Runner. And here I just want to give you a quick preview of what Harvard Runner is. And this is, again, this is another GPU cluster. And we put Harvard Runner under the Spark Deep Learning pipelines package, and you can just import it there. And then for the runner, it kind of help you to run a Harvard job and help you to integrate that job perfectly with a Spark cluster. And you can say, I want to create a Harvard Runner instance with 2 workers. And then, so if you are familiar with Harvard, what Harvard does is to, you only need to just put a few Harvard plugbook code into an existing single machine training code and to distribute the workload. So the code I'm showing here is basically copied from the Harvard example, how to do distributed training with TensorFlow on MNIST. So I only made some really minor modifications and like this run method signature. So this is how you run Harvard, and you put this Harvard init. And then when you talk about this reach the optimizer, you wrap the existing TensorFlow or Keras optimizer with Harvard distributed optimizer. And then with Harvard, will automatically merge the model updates to gradient updates and update the model in a synchronous way. And in this approach, you can actually get very good scalability and for distributed deep learning training. I'm going to skip the rest of the code. You can follow the tutorials from Harvard example or wait for us to release the tutorials for Harvard Runner. We'll show you some end-to-end examples for TensorFlow, Keras, and PyTorch. And after you finish the Harvard modification to our existing single machine training code, we only need a function from you, a Python function from you that does the training, and then you can use the hardware runner to easily distribute the job as a Spark job. So you can see, well, it start running this job, and then, well, you can see the training logs showing up in the Spark log. And as a user, you don't need to handle, for example, the MPI commands. You don't need to know where the worker IPs are. So we try to have everything for you. And this feature is built upon the barrel execution mode and in Spark 2.4. So just a demo to show how we can use barrel execution mode to provide the best-in-class deep learning and big data integration. So, yep, let me end the screen sharing and go back to the slides. I think, yeah, that's the end of my talk, and I'm now ready to take questions.
Well, Shangri, thanks for that excellent presentation. So we'll get started with today's Q&A session, and I want to thank the audience for their participation. Had a lot of questions that have come in, and we'll do our best to get through all of them in the time remaining. So during this Q&A session, I'll leave up this screen with contact information for Shangri if you'd like to contact him following today's event. So let's get started. Shangri, we've had a bunch of interesting questions come in from the audience. Let me start here, particularly on your last comment. The question is the hydrogen Horvath barrier mode and DL integration limited to TensorFlow, or are you supporting other frameworks like MXNet?
So to answer this question, I want to separate the framework. First one is Harvard. Harvard is a distributed training framework developer at Uber. So it supports TensorFlow, and it supports Keras and PyTorch. And the Hydrogen is basically in the barrel execution mode. It doesn't care about what distributed deep learning framework you are using. So it only provides kind of a job scheduling that can fit into this distributed deep learning training communication pattern. So you can easily put Harvard on top of barrel execution mode and then run distributed deep learning with TensorFlow, PyTorch, and the Keras on top. So, and also if you want to use, for example, distributed MXNet, it's also feasible because we provide you the worker IP addresses, and you can just say set up this integration. And same story for distributed TensorFlow, and where you need to set up where is the server, where the workers, right? So, and I think, yeah, so it's built on different layers, and you can just say stack them up and make them work.
Okay, well, thanks for that clarification. Now, kind of along that same refrain, is what you've described, is that integrated with Spark ML pipelines also?
So currently, the barrel execution mode lives in Spark core, and there are multiple ways to integrate with Spark ML pipelines. And first one, once we finish the optimized data exchange project, and then, well, Spark ML pipelines, you can use that for making model predictions. You can imagine you define a model, wrap the model as a Spark ML pipelines transformer, and then with the optimized data exchange, you can achieve really good performance compared to single machine model inference. And currently, I would say the performance won't be ideal because this data exchange issue. And for distributed deep learning training, and currently the estimators in MLlib is not integrated with the barrel execution mode, but we do expect people to just implement this integration either inside Spark or outside Spark as a third-party package, and so that's definitely doable. And after you implement this as for example, implement distributed deep learning training as a Spark ML pipeline estimator, you can then use the cross validation for to tune your model hyperparameters. And currently, there's no integration with Spark, but I don't see any blockers for it.
Oh, terrific. Oh, thanks for that clarification. Now, the audience was curious. In your earlier demo, you had 4 GPUs running, and they're wondering, was that part of a Spark cluster or was it part of a remote GPU machine?
So in my demo, it's not a remote GPU machine, and we're using AWS for this demo, and we are using GPU instances. In the demo, I believe I use P2 X large. It has a 1 GPU installed on every worker.
Okay, all right, terrific, thank you. Now, difference between CPU and GPU training. What are the differences between implementing this distributed training on CPUs versus GPUs, and does your procedure support both of those?
So basically, it's computation, and for training, usually GPU can provide you a faster state. But for distributed deep learning training, you also care about the communication and the computation trade-off, right? So because you need to pass over the updates among the deep learning training workers, and there will be introduced some communication overhead. And so basically for your job, my recommendation is first try on a small number of nodes, and you can use either CPU or GPU and test the acceleration and see if you can achieve, for example, 70 or 80% efficiency on a distributed cluster. And then you can just definitely, you can balance the communication and computation and decide whether you use CPU or GPU. For CPU, we definitely recommend using the MKL DNN enabled TensorFlow or just other deep learning frameworks supporting CPU acceleration. And so for model inference, it will be a different story because the communication overhead is most significant. And you always need to read the data in for every single record, right? So, and per record computation is not that big. And in that case, you need to carefully test CPU performance and GPU performance, and to make sure you don't just waste expensive GPU resources, right? So, but for training, we usually find GPU is more cost effective.
Okay, that makes perfect sense. Makes perfect sense. Now, here's the, a final question, maybe where we should have started, and that is, do you have any benchmarks that you can share on the performance improvements that you've created using hydrogen?
So here is first talk about distributed deep learning training. And we tested the performance, and essentially it's the same performance if you run this MPI job or Harvard directly on the same cluster, or just a cluster setup consisting the similar node types. So because it runs as an embedded Spark job, but inside it, it's still the same distributed deep learning training job, right? So there's no kind of data exchange happening between the deep learning training and Spark. And Spark is here, it plays a role as just a job launcher and monitor the job and recover it in case of failures, but the performance, they're the same. And for model inference, and currently, we kind of in the early stage of this project, and we are going to measure, doing the benchmark and measure the performance, the current performance of some baseline approaches, and then see how we can improve them.
Well,
so for training,
yeah, go ahead.
Oh, so for training, you can just a couple websites you can check, and the first one is definitely the Harvard GitHub repository, and there's a benchmark page. You can see the performance numbers there. And I believe for major cloud providers like AWS and Azure, they also publish a benchmark with Harvard. We did the performance comparison, and the numbers are the same.
Okay. Oh, thanks very much for that. Now, by the way, the audience is asking, with respect to hydrogen, can I use hydrogen only with Databricks, or can I do the things that you've described here without using Databricks?
It's optional. So hydrogen, especially the barrier execution mode implemented in Spark 2.4, is available to all the users. And with the tools, just the interface implemented, I believe it's very feasible for you to integrate with Harvard or other distributed deep learning frameworks. And the Harvard Runner we implemented on Databricks, and say we just make it super easy and more polished and for Databricks users. But it's definitely optional for you to leverage Project Hydrogen.
Well, Shanri, thank you. Those were some great answers to some very good questions. For those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Shanri and the Databricks team so they can follow up with you following today's webinar. Now, I have just a few quick announcements. If you'd please mark your calendars for November 6th, that's our next DSC webinar, which will be Data Lake Advances in the Age of Operational Machine Learning and AI. Also remember that today's taping will be available for on-demand viewing later today, and you can find that on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions. A special thanks again to Databricks for their sponsorship, and particularly our speaker today, Shanri Meng, for his insight into today's topic. This is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on November 6th. Have a great day.